All right, so this is where we were left off last time. All right, so the S&P waves give us a picture, and this is kind of a nice cutaway showing, of course, there's the crust of the Earth. All right, so the crust varies in thickness, anywhere from roughly 20 to about 70 kilometers in thickness. So it's it's not very thick at all compared to the entire Earth, which has a distance to the center of about 6,400 kilometers. All right, so roughly 6,400 kilometers. All right, so anyhow, notice the biggest part of the Earth is the mantle, right? As far as volume goes, right? Is this the mantle? The mantle is huge, um, and that's in fact where a lot of the minerals were formed, that we use around on the Earth. Um, anyhow, the mantle. And then, this is not we're not going to get too far into the geology of it. We're just a little bit. The big idea here is, of course, we know the Earth better than any other planet. And what we're going to do is we're going to compare the other planets to the Earth. And in fact, we'll even compare the gas giant planets to the Earth. Um, at least, as for what we know of some of those planets. All right, so we'll get into that stuff later. All right, then of course there's the liquid, the liquid core where it's iron and nickel, and then that what happens is that iron and nickel, it becomes yeah. Let me talk about that a little bit. Right. So remember, before we did the density of the Earth is about 5.5 grams per cubic centimeter. So right at the surface of the Earth, you have water, which has a density of about 1, rocks that are on average about a density of 3, um, and so the density of things, the Earth's gravity squeezes stuff, squeezes material uh, greater and greater, and then when you get towards the center, this iron and nickel turns into a solid, right? And we know that it's solid, as I mentioned before, as the P waves pass through. Remember, the P waves can only go through the liquid outer core. They will bend when they pass through the solid core, and we've been measuring that bending for a long time, so we know what the size of this is. All right, so let's see. If you looked at it from the side, this little cutaway right here, um, the inner core is about 1,200 kilometers from the center to and then this outer core. Um, Remember, this is like a shell of material. Um, is from 1,200 to 13. I'm sorry, 3,500 kilometers, and then most of it is mantle, um, and then just a little narrow part is the crust, right? Which includes the ocean. The oceans sit on top of the crust. All right. The mantle is made of this material called olivine. It's kind of a greenish color. It's of course there's the silicate, but it's magnesium and iron silicate, um, and there's all sorts of minerals and such that come from the mantle. Um, and you might say, well, how does the mantle material make it to the surface? Of course, that's volcanoes, right? That's exactly what happens. And some of that material comes up and gets distributed on the surface of the Earth during volcanic activity, and we get things like this olivine, or actually it's usually quite different from the olivine. It you get things like feldspar and things like that, which are other types of well, yeah, other types of minerals. All right. So anyhow, I mean, there's all sorts of minerals that get formed in the interior of the Earth, and come out through the volcanic activity. All right. So we'll just leave it at that. Again, this is not an entire. We're going into a little bit of the geology, but not too deep. So the Earth, when it was formed, was there was lots and lots of material, very dense material like iron and nickel, and much less dense material like silicates. And so what happened with the Earth is it differentiated. All right. So the differentiation it happens because of gravitation. Gravitation will cause more dense material to end up towards the center, and less dense material will end up here. Let's go back to more dense material will end up at the center, like iron and nickel, and then less dense material out by the core, out in the core of, or sorry, not the core, the crust, and even in the mantle is less dense than the core. The crust is less dense than the mantle. Remember, the whole of the Earth has a density of 5.5 grams per cubic centimeter, but of course that varies throughout the Earth. All right, that 5.5 is just the average. That's the average of the entire planet. It's also known as the bulk density. All right, so differentiation is just gravity acting on more dense material. More dense material end up at the center, less dense at the core. And so here's the example. I love this example. So let's say you had some mint chocolate chip ice cream, right? And you buy like a half gallon of mint chocolate chip ice cream, and it was in the manufacturing process. It was all mixed up, right? So the mint, you're not going to want to dig into your ice cream and have the mints all at the bottom or anything like that. So let's say when it was made, the mint chocolate chips were all was distributed throughout the ice cream. Now, if you took the ice cream, let's say you just took this half gallon ice cream, you set it on the counter, and somehow something distracted you, and you walk away from it, and it has time to melt, right, to come to room temperature. And so what will happen as the ice cream begins to melt, the mint chocolate chips, which were distributed evenly throughout the ice cream, will end up at the bottom, right? Because they are more dense. That's the idea of differentiation. That's the basic idea of differentiation. And the same thing happened to the Earth, right? So the other thing is, of course, the Earth had to be molten, right? The entire planet, very very early in the stages of the Earth heated up to the melting point of rock. The entire planet heated up to the melting point of rock, and of course it's still that hot inside of the Earth, deep inside the Earth. But the entire thing was melted, and so the most dense material ended up at the core, and then less and less dense as you get towards the crust. That's called differentiation, and it's just a property of gravity. That's exactly what happens. All right, so now nobody's actually measured the core of the Earth, but so using physics techniques. Okay, so I'll just put it that way. Using what's called thermodynamics, we estimate that the very center of the Earth is around 6,500 Kelvin. Kelvin is the absolute scale. Just to let you know, like room temperature is about 300 Kelvin. just just to just to let you know, like the freezing point of water is 273 Kelvin. Um, so that's pretty cold. And then room temperature is right around 300 Kelvin or so. All right, so just to let you know, the surface of the sun, our star, is at about 6,000 Kelvin. So the interior of the Earth is actually a little bit warmer than the surface of our sun. Now that's just the surface of the sun. It gets much hotter towards the center of the sun, where uh, nuclear fusion is taking place. That's a different story. All right, now, what keeps the interior of the Earth hot? One thing is just from the original formation of the Earth. When the Earth formed, there were lots and lots of impacts, and that those impacts melted any rocky material would have melted as more and more things rained down on the very early Earth, and that heat gets trapped inside of the Earth. The other thing the main two things are the original the original formation of the Earth that heated the Earth, and that's still around. But the other thing is radioactive decay. When certain atoms, and I kind of mentioned this a little bit earlier, certain atoms are unstable, and they are they're said to be radioactive. And when something is radioactive, like for example uranium-238, which is the most common form of uranium that you find on the planet Earth, when uranium-238 undergoes a radioactive decay, it changes into a new atom, but in addition to that, it releases heat. Right. So and all radioactive substances release heat as part of what they do. All right. So that's actually the opposite of what's going on in the sun. The sun is converting lighter elements on the periodic table into heavier elements. Mostly hydrogen turned into helium, but radioactivity generally takes higher mass elements, and then there's a process called fission where those higher mass, they got to be unstable though. Not any one of them can do it, but they have to be unstable, and they will decay into less massive things. But in the meantime, they release heat, and that's happening all the time inside of the Earth. And the other thing about this is, if you looked at like all the different solids, right? So imagine a cube, and you compare the surface area to the volume of a cube, and then like you took the Earth as the Earth, which is almost perfectly spherical. If you compared the ratio of the surface area of the Earth to its volume, to its three-dimensional space that it takes up, the surface area to volume is huge compared to like a cube, right? A cube would if it was hot in the interior, if it was hot, it would radiate that heat out into space very, very quickly. Whereas the Earth, because it has so much greater volume than it does surface area, right? Because of the fact that it's a sphere, it retains heat. It holds on to heat very, very efficiently. I mean, like this efficiently. 5 to 10 million, right? That's basically that ratio right there. So it's doing a good job of holding on to the heat that was caused by the original formation and caused by radioactive decay, which is going on all the time inside of the Earth. All right. So this is our first stab at if you will, at dating the Earth. How old is the Earth? All right. It turns out to be 4.5